Hello, everyone. I'm excited to welcome you to today's presentation. We'll be exploring the fascinating topics of light, specifically reflection and refraction. The slide you see now is our title slide. Light, reflection, and refraction. Over the course of this presentation, we'll cover how light behaves when it bounces off surfaces and passes through different mediums. We'll look at the fundamental principles and some real-world applications, too. Let's get started and dive into the world of light. Let's take a moment to look at slide 2, which introduces the fundamental concepts related to spherical mirrors and lenses. We begin with light, the basic phenomenon that makes all of this possible. Understanding how light behaves is essential to grasping how mirrors and lenses form images. Next, we explore the reflection of light, which is the foundation of how spherical mirrors work. Reflection is when light bounces off a surface, following specific rules that we'll examine later. Moving forward, we delve into the reflection by spherical mirrors, highlighting how their curved surfaces influence the direction of reflected rays. To analyze these effects systematically, we use the new Cartesian sign convention for spherical mirrors, which helps us determine the correct signs for distances and focal lengths in our calculations. Then, we consider the reflection of light in more detail, understanding how images are formed through this process. This naturally leads us to the terms used when studying spherical mirrors, key vocabulary that will underpin our entire discussion. We also look at the uses of spherical mirrors, which are everywhere, from rearview mirrors in cars to telescopes, showing their practical importance. To deepen our understanding, we examine the images formed by concave and convex mirrors, noting the differences in how they produce real or virtual images. Similarly, we explore the images formed by convex and concave lenses, expanding our knowledge of how lenses manipulate light to form images. Understanding refraction, the bending of light as it passes through different media, is crucial here because both lenses and mirrors rely on this phenomenon to function properly. We then analyze refraction specifically by spherical lenses, which helps us understand their focusing properties. This leads us to the study of the power of a lens, a measure of how strongly a lens converges or diverges light. Finally, we introduce the lens formula and the mirror formula, fundamental equations that relate object distance, image distance, and focal length, allowing us to quantitatively analyze image formation in spherical lenses and mirrors. All these concepts are interconnected, forming a comprehensive framework that explains how light interacts with curved surfaces, enabling us to understand and predict the behavior of optical devices. Light is a form of energy that plays a crucial role in our everyday lives because it helps us see objects around us. When light hits an object, it reflects off its surface, and that reflected light travels to our eyes. That's how we perceive and recognize objects. It's fascinating to think that light travels in straight lines, which explains many natural phenomena. For example, the formation of shadows occurs because light is blocked by an object, creating a dark area. We also see images formed by mirrors and lenses, where light is reflected or refracted to produce clear images. Light bending when passing through different mediums, like water or glass, is another interesting behavior. This bending, called refraction, is responsible for the twinkling of stars and the beautiful colors of a rainbow. So, in essence, light is not only essential for vision, but also responsible for many phenomena we observe in nature. Understanding these basic properties of light helps us appreciate the way it shapes our visual world. When light hits a highly polished surface like a mirror, most of it doesn't pass through or get absorbed. Instead, it bounces right back into the same medium. This phenomenon is what we call reflection of light. Reflection is essentially the process where light changes direction after hitting a surface, and it's a key concept in understanding how we see objects and how optical devices work. Remember, the more polished and smooth the surface, the more effectively it reflects light. This idea ties into the broader theme of how light interacts with different surfaces, helping us understand everything from everyday reflections to complex optical systems. In this slide, we're focusing on a fundamental concept in the laws of reflection. The first key point is that the incident ray, the reflected ray, and the normal to the mirror at the point of incidence all lie in the same plane. This means that when light hits a mirror, everything involved, the incoming light, the reflected light, and the perpendicular line to the surface, are all in one flat surface, which helps us understand how reflection works in a straightforward way. Next, we have Law 2, which states that the angle of incidence is equal to the angle of reflection. This is a crucial rule because it explains why the light bounces off the mirror in a predictable manner. When the incident ray hits the mirror at a certain angle, the reflected ray leaves at the same angle, relative to the normal. Together, these laws form the foundation of understanding how mirrors and reflective surfaces behave. They highlight that reflection isn't random, but follows specific, consistent principles. Recognizing these points helps us better grasp more complex optical phenomena later in the presentation. All right, let's take a closer look at the image formed by a plane mirror. First, the image is at the same distance from the mirror as the object itself is in front of it. This means if you stand a meter in front of the mirror, your image appears 1 meter behind the mirror surface. Next, the image is laterally inverted, which is a key feature of plane mirrors. If you raise your right hand, your image raises its left hand, creating this mirror reversal. Also, the image is the same size as the object, maintaining the original dimensions. So, there's no magnification or reduction here. It's a true-to-life representation in size. Another important point is that the image is virtual. That means you can't project it onto a screen because it doesn't actually exist there. It only appears to be behind the mirror. And finally, the image is erect. Unlike some images formed by other mirrors, which can be upside down, this one maintains the same orientation as the object. All these points highlight the unique way plane mirrors form images. It's a combination of position, size, orientation, and the virtual nature that makes them so fascinating and useful in everyday life. Let's take a closer look at spherical mirrors. A spherical mirror is essentially a part of a hollow sphere, which means it's curved in a specific way. There are 2 main types of spherical mirrors. The first is the convex mirror, where the reflecting surface curves outward. Imagine a mirror that bulges towards you. When light rays that are parallel to the principal axis hit this mirror, they diverge after reflection. Interestingly, these rays appear to come from a point behind the mirror, which is a key concept in understanding how convex mirrors work. The second type is the concave mirror, which has its reflecting surface curved inward, like the inside of a bowl. When parallel rays of light strike a concave mirror, they converge at a point on the principal axis after reflection. This convergence point is crucial because it forms the basis for how concave mirrors are used in applications like telescopes or headlights. So, in summary, spherical mirrors are versatile tools with 2 main types, convex and concave, that behave differently with light. Understanding these differences helps us grasp many optical phenomena and practical uses of mirrors in everyday life. Let's talk about the distance between the pole and the principal focus. In a spherical mirror, the radius of curvature is actually twice the focal length. So, if you know the radius of curvature, you can find the focal length by simply dividing by 2. That's r equals 2 times f, or conversely, f equals r divided by 2. Now, moving on to the focal length itself. In a concave mirror, when light rays travel parallel to the principal axis, they reflect and meet at a point called the principal focus, which is on the same side as the reflective surface. Conversely, in a convex mirror, those same parallel rays diverge after reflection, but they appear to originate from a point behind the mirror, also called the principal focus. Next, let's look at the principal axis. This is a straight line passing through the center of curvature and the pole. It essentially helps us understand how rays are reflected and where they converge or seem to diverge from. The pole, marked as P, is simply the center point at the surface of the mirror itself, and the radius of curvature, or CP, is the radius of the sphere of which the mirror is a part. Finally, the center of curvature, marked as C, is the actual center point of that sphere. Understanding these terms is key because they form the foundation for analyzing how spherical mirrors work and how images are formed. Let's explore how light behaves when it interacts with spherical mirrors. Starting with oblique reflection, when a ray of light hits the mirror at an angle directed at the pole, it reflects obliquely, making equal angles with the principal axis. This is a fundamental property of both concave and convex mirrors. Moving on to focus reflection, in a concave mirror, if a ray passes through the focus after reflection, it becomes parallel to the principal axis. Conversely, in a convex mirror, a ray directed towards the focus after reflection also runs parallel to the principal axis. This demonstrates how rays behave differently depending on the mirror's shape, but follow related principles. Next, for center of curvature reflection, in a concave mirror, a ray passing through the center of curvature reflects back along the same path. Similarly, in a convex mirror, a ray directed towards the center of curvature reflects back along its original direction. These behaviors help us understand image formation in these mirrors. Finally, in the case of rays parallel to the principal axis, a ray incident on a concave mirror reflects through the focus, while in a convex mirror, a parallel ray appears to diverge from the focus after reflection. These key points about spherical mirrors highlight how light interactions govern the formation of images and help us understand their optical properties. When the object is between F and P, the image is formed behind the mirror. It is enlarged, virtual, and erect. This is a key point because it shows how the position of the object relative to the focus and pole affects the image characteristics. Next, when the object is exactly at F, the image is formed at infinity. It becomes highly enlarged, real, and inverted. This illustrates how placing the object at the focus causes the rays to diverge infinitely, creating a very large image at infinity. Moving on, when the object is between C and F, the image is formed beyond C. It is enlarged, real, and inverted. This demonstrates that as the object moves closer to the focus from beyond the center of curvature, the image becomes larger and moves further away from the mirror. When the object is at C, the image is formed at C as well. It is the same size as the object, real and inverted. This is a special case where the object and image are equal in size and located at the same point, highlighting a key property of the mirror. Next, when the object is beyond C, the image is formed between C and F. It is diminished, real, and inverted. So, as the object moves further away past the center of curvature, the image gets smaller and closer to the focus. Finally, when the object is at infinity, the image is formed at the focus. It is highly diminished, real, and inverted. This tells us that very distant objects produce images at the focus point, which are tiny but still real and inverted. All these points help us understand how the position of an object relative to a concave mirror determines the nature, size, and position of the image formed. When the object is located between infinity and the pole of the mirror, the image that forms will actually be behind the mirror. This image is typically smaller than the object, meaning it is diminished, and it's also virtual and erect, which means it appears upright and behind the mirror rather than on a screen. Now, if we consider when the object is at infinity, the image forms at the focus, F, behind the mirror. In this case, the image is highly diminished, meaning it's very small, and it remains virtual and erect, just like in the previous scenario. Understanding these concepts helps us grasp how convex mirrors form images. They always produce virtual, erect, and diminished images, which is why they're great for security and rearview mirrors in vehicles. Recognizing where the image forms relative to the object gives us insight into the behavior of convex mirrors across different situations. Large concave mirrors are quite fascinating because they have the ability to concentrate sunlight. This means we can focus a lot of solar energy onto a small area, which is very useful in solar furnaces where heat is needed for various processes. You might also see concave mirrors used as shaving mirrors. Because of their shape, they can produce larger, clearer images of your face, making it easier to see details while shaving. Dentists also use these mirrors to get a bigger view of your teeth. The mirror's shape helps them see small areas clearly, which is essential for accurate diagnosis and treatment. In addition, concave mirrors are found in torches, searchlights, and vehicle headlights. They help produce parallel beams of light, which are powerful and focused, allowing us to see far distances effectively. So, as you can see, concave mirrors have a wide range of practical uses, from energy concentration to everyday personal care and safety. They are definitely an important part of many optical devices we rely on daily. Convex mirrors are commonly used as rear-view mirrors in vehicles. You'll notice that they provide an erect and diminished image of objects, meaning the objects appear upright but smaller. This is very useful for drivers because it allows us to see more of what's behind us without having to turn our heads too much. One of the key advantages of convex mirrors is that they have a wider field of view compared to flat mirrors. This broader perspective helps us detect vehicles and obstacles coming from the sides much more effectively, enhancing safety. So, in the context of our overall discussion on mirrors, convex mirrors are essential in everyday life, especially in vehicles, because they maximize our visibility and minimize blind spots. Let's go over the new Cartesian sign convention for spherical mirrors. First, the height measured downwards perpendicular to the principal axis is considered negative. Conversely, if the height is measured upwards, it is positive. When measuring distances along the principal axis, all measurements to the right of the pole are positive, while those to the left are negative. It's important to remember that all distances are measured from the pole, which serves as our reference point. Now, in our setup, the object is always placed on the left side of the mirror, and the light from the object travels from left to right. These conventions help us systematically determine the sign of various quantities, making the analysis consistent and straightforward. Connecting these points to the overall theme, understanding this sign convention is crucial in accurately drawing and analyzing spherical mirror diagrams and their associated equations. Let's start by looking at the first equation, m equals hi over ho, which also equals v over u. This tells us that magnification can be expressed in terms of the heights of the image and object, or in terms of their distances from the mirror. The key point here is that magnification is a ratio, and it helps us understand how much larger or smaller the image appears compared to the object. Next, I want to emphasize that the magnification for spherical mirrors is also related to the object distance and image distance, which are represented by u and v, respectively. So, when we talk about magnification, we're essentially comparing the heights of the image and object, but it's also connected to how far the object and image are from the mirror. Moving on, there's the mirror formula for spherical mirrors, which is 1 over v plus 1 over u equals 1 over f. This formula is fundamental because it links the object distance, image distance, and the focal length of the mirror. It's a quick way to determine one of these parameters if you know the other two. Overall, these concepts, magnification and the mirror formula, are central to understanding how spherical mirrors form images and how those images relate in size and position to the original object. When light travels obliquely from one transparent medium into another, it doesn't just pass straight through, it actually bends. This phenomenon is known as refraction. Now, the key idea here is that the bending depends on the nature of the two media. When light moves from a rarer, or less dense, medium into a denser one, it bends towards the normal line. Conversely, if it travels from a denser medium to a rarer one, it bends away from the normal. Understanding this bending behavior helps explain many optical phenomena we see around us, like the way objects appear distorted in water or how lenses work. So, refraction is fundamentally about how light changes direction when crossing different transparent materials, and this change in direction depends on the density of those media. When a ray of light passes through a rectangular glass slab, it experiences bending at 2 points. First, at the air-glass interface, the light slows down and bends toward the normal. Then, as it exits the glass and enters the air again, it bends away from the normal. What's interesting here is that despite these bends, the emergent ray ends up parallel to the incident ray. However, it is displaced through a certain distance, which is an important concept in understanding how light behaves in such media. This phenomenon highlights how refraction causes both directional change and displacement, which ties into the broader theme of how light interacts with different materials. Now, let's look at the key concept here. The ratio of the sine of the angle of incidence to the sine of the angle of refraction remains constant for a specific color of light passing through a particular pair of media. This means that if we know the angles, we can predict how light will bend as it moves from one medium to another. This relationship is what we call Snell's law of refraction. Mathematically, it's expressed as the ratio of sin I to sin R being equal to a constant. Here, sin I is the sine of the incident angle, and sin R is the sine of the refracted angle. This constant actually depends on the media involved and the color or wavelength of the light. It's also important to remember the geometric arrangement involved. The incident ray, the refracted ray, and the normal to the interface at the point of incidence all lie in the same plane. This ensures that the angles are measured consistently and helps us understand the bending behavior more clearly. So, in essence, Snell's law helps us quantify how light changes direction at an interface, and it forms a fundamental part of understanding how light behaves as it travels through different transparent media. Now, let's take a closer look at the concept of the refractive index. The first part, n sub 21, is the relative refractive index of medium 2 with respect to medium 1. It's expressed as the ratio of the speed of light in medium 1 to the speed of light in medium 2. So essentially, it tells us how much slower or faster light travels in one medium compared to another. Moving on, the general formula for the refractive index, n equals c over v, where c is the speed of light in air or vacuum, and v is the speed of light in the specific medium. This ratio is crucial because it quantifies how much light bends or refracts when passing from one medium to another. Understanding both the absolute and relative refractive indices helps us analyze how light interacts with different materials, whether it's glass, water, or other transparent substances. These concepts are fundamental in optics, as they influence phenomena like lens design, optical fibers, and even the way we see objects. So, in summary, the refractive index connects the speed of light in various media to how light behaves when it encounters different materials. It's a key factor in understanding optical properties and designing systems that rely on precise light manipulation. Let's take a closer look at how different types of spherical lenses affect light. First, consider the concave lens, which is thinner in the middle and thicker at the edges. When light rays that are parallel to the principal axis pass through this lens, they diverge after refraction. To understand this better, we trace these diverging rays backward, and they appear to originate from a single point on the same side of the lens, called the principal focus. This diverging behavior is key to how concave lenses form images. Now, moving on to the convex lens, which is the opposite in shape, thicker in the middle and thinner at the edges. When parallel rays of light pass through a convex lens, they converge or meet at a point on the principal axis, known as the focal point. This converging property is essential for many optical devices like magnifiers and cameras. Finally, let's connect these ideas to the broader concept of spherical lenses. A spherical lens is simply a transparent material with two surfaces, at least one of which is spherical. These are mainly of two types, convex and concave, and their shape determines whether they converge or diverge light. Understanding these fundamental properties helps us grasp how various optical systems work, whether for focusing light in cameras or correcting vision. Now, let's discuss what happens when light passes through different types of lenses. In both convex and concave lenses, a key point is that any ray of light passing through the optical center goes straight through without any deviation. This is crucial because it means the optical center acts as a sort of neutral point for the light rays. Moving on, in a convex lens, if a ray of light passes through the focus after refraction, it will come out parallel to the principal axis. Conversely, in a concave lens, A ray directed towards the focus after refraction will also emerge parallel to the principal axis. This symmetry is quite interesting because it shows how these lenses manipulate light differently, but with similar underlying principles. Additionally, when a ray of light travels parallel to the principal axis and enters a convex lens, it refracts through the focus on the other side. For a concave lens, the same initial condition causes the light to diverge, as if it's coming from the focus on the same side of the lens. These behaviors are fundamental to understanding how lenses form images, and they tie back to the overall theme of how spherical lenses bend and focus light in different ways. When the object is between f1 and O, the image is formed on the same side of the lens. It is enlarged, virtual, and erect. This means that the closer the object gets to the lens, but still between f1 and O, the bigger the image appears on the same side as the object, and it remains upright and virtual. Now, if the object is exactly at f1, the image is formed at infinity. In this case, the image becomes highly enlarged, and interestingly, it is real and inverted. So, at this specific position, the lens creates a very large, real, and upside-down image far away from the lens. Next, when the object is between 2f1 and f1, the image shifts beyond 2f2. Here, the image is enlarged, real, and inverted, which is typical for objects placed between these focal points. The size of the image increases, and it forms on the opposite side of the lens, beyond twice the focal length. If we place the object exactly at 2f1, the image forms at 2f2. In this case, the image is the same size as the object, real and inverted. This is a key point because it shows a simple, proportional relationship when the object is at this specific point. Now, if the object moves beyond 2f1, the image forms between f2 and 2f2. In this scenario, the image is smaller, diminished, still real and inverted. The image moves closer to the focal point on the other side as the object moves further away. Finally, when the object is at infinity, the image is formed at the focus, f2. In this extreme case, the image is highly diminished, but it remains real and inverted. This illustrates how distant objects produce very small images at the focal point. Understanding these positions helps us grasp how convex lenses form different types of images depending on where the object is placed, which is fundamental for applications like cameras, microscopes, and eyeglasses. When the object is located between infinity and f1, the image formed behaves in a specific way. It appears on the same side of the lens as the object, but interestingly, it forms between f1 and O. This image is diminished, meaning it's smaller than the object, and it's virtual and erect, so it maintains the same orientation. Now, if we consider the object at infinity, the situation simplifies a bit. The image is formed right at the focus, f1, on the same side of the lens. In this case, the image is highly diminished, so it's very small and still virtual and erect. These points are key because they highlight how the position of an object relative to the focal length influences the image's position, size, and nature when dealing with concave lenses. It's a fundamental concept that helps us understand the overall behavior of light and image formation through lenses. Now, let's talk about the sign convention for spherical lenses. The key thing to remember is that it's very similar to what we saw with spherical mirrors. But here's the twist. The distances are measured from the optical center, which we label as point O. So, when we determine whether a focal length is positive or negative, we're measuring from this point. For convex lenses, which are converging lenses, the focal length is considered positive. That's because the focal point is on the opposite side of the lens from where the light is coming. Conversely, for concave lenses, which are diverging, the focal length is negative, since their focal point lies on the same side as the incoming light. This sign convention is really important because it helps us analyze and predict how lenses form images, just like with mirrors. It keeps everything consistent and clear, especially when dealing with complex ray diagrams or optical systems. So always remember, the focal length sign tells us about the lens type and how it interacts with light. Now let's look at how magnification is expressed in the context of spherical lenses. The formula m equals high over ho, where m represents the magnification, high is the height of the image, and ho is the height of the object. This ratio tells us how much larger or smaller the image is compared to the object. It's important to understand that magnification isn't just about size. It also relates to the distances involved. Specifically, the same ratio applies to the object distance u and the image distance v, so m equals v over u. When dealing with spherical lenses, the magnification is essentially how tall the image appears relative to the object. If the image is upright and magnified, that ratio m will be greater than 1. If it's inverted or reduced, the ratio will be less than 1. Now moving on to the lens formula itself, which is fundamental. It states that 1 over v equals 1 over u plus 1 over f, where u is the object distance, v is the image distance, and f is the focal length of the lens. This formula is crucial because it links all three key variables, allowing us to determine any one if we know the other two. It's the backbone of understanding how spherical lenses form images, whether they are real or virtual. So, in summary, these concepts, magnification and the lens formula, are central to understanding how lenses manipulate light to produce images. They help us predict and analyze the behavior of light in optical systems. The SI unit of power for lenses is called the diopter. Abbreviated as D1, diopter represents the power of a lens that has a focal length of exactly 1 meter. Now, when we talk about the power of a convex lens, we describe it as positive, which we write as plus. Conversely, the power of a concave lens is negative, and we denote it as. To understand this relationship better, there's a simple formula. P equals 1 divided by F, where P is the power in diopters and F is the focal length in meters. So, if you know the focal length, you can easily find the power by taking its reciprocal. Similarly, if you know the power, you can find the focal length by taking 1 divided by the power. This concept is fundamental because it links the physical characteristic of a lens, its focal length, to its optical strength or power. Remember, the shorter the focal length, the greater the power of the lens, and vice versa. This reciprocal relationship helps us understand and compare different lenses efficiently, especially in applications like glasses, microscopes, or cameras. So, in essence, the power of a lens is all about how strongly it converges or diverges light, and the diopter provides a standardized way to measure and communicate that strength clearly.